This video is going to continue the introduction to CMOS logic gates, and it assumes some knowledge of De Morgan's law and Boolean algebra. So CMOS transistor operation. To review, we have NMOS transistors and PMOS transistors. For the NMOS transistor, we can think of it as a binary switch that's closed or connected if the gate voltage is high and the source voltage is low. So when we talk about high and low voltages, let's review here. Quick a second. High VDD, or high voltage, implies a logic 1, and a low voltage, VSS, implies a logic 0. So the NMOS transistor is a binary switch that's closed or connected if the gate voltage is high and the source voltage is low. When closed, the drain and source are connected and the current can flow from drain to source, like so. For the PMOS transistor, it's a binary switch again that's closed if the gate voltage is low. So notice the difference here. NMOS has a high voltage at the input or gate here, and for the PMOS we expect a low voltage at the input or gate, and it assumes that the source voltage must be high, and current will flow from source to drain in this case. So PMOS and NMOS transistors applied here in an inverter. We can think of them as electrically controlled switches, and in this circuit we've connected the PMOS transistor here and the NMOS transistor here in a series format and given them both the control signal A as input. We have our output signal Y here. The PMOS has what's called a bubbled input. The bubbled input can be thought of here as an inversion. So anytime you see a bubble, either in the transistor or on a logic gate, think of an inversion. In CMOS logic, the Y must always be tied to either a high voltage or a low voltage, logic 1 or logic 0. There are some minor exceptions to this, which we will come to in later lectures. So more formally, when we wish to think about implementing Boolean logic in digital circuits, we need to think about series circuits here and parallel circuits here. So NMOS and PMOS use different inputs to indicate a connection or disconnection. Let's look at how NMOS in series or parallel compare with PMOS transistors in series or parallel. First, we'll look at series NMOS. When we have NMOS connected in series, we want to think about an AND operation. So in this circuit here, we have a connection of two NMOS transistors in series with gates G1 and G2, and the nodes connected are A and B. Now, G1 and G2 represent the inputs. If G1 is, or G2, if either G1 or G2 are 0, then there will be a disconnection between A and B. This is represented by these three cases here: 0, 0, 0, 1, 1, 0. So if G1 or G0 is 0, then the switch is not connected. But if it's 1, then the switch is connected. The only time A and B are connected is when G1 is equal to 1 and G2 is equal to 1 as well. So here. So if G1 is 1 and G2 is 1, so represented by a multiplication here. For all three other cases, where either G1, G2, or both are equal to 0, there is a disconnection between nodes A and B. If we look at series PMOS transistors, then there is a connection between A and B if and only if both the gate voltages, G1 and G2, are equal to 0. Because a PMOS is on or connected if and only if the input is 0. So if G1 and G2 are both 0, in this case here, then there's a connection from A to B and current flows. If either if either G1 or G2 are equal to 1, then there is a disconnection between nodes A and B. So either G1 is 0 or G1 is 1 or G2 is 1 or both, in which case there is no connection. So this can be written as G1 prime, G2 prime. Now, an interesting thing we can do by De Morgan's law is characterize this as an OR symbol by taking the inversion out. So this is G1 ORed with G2 and primed. So there's a connection if either G1 is true or G2 is true. So let's look at here the parallel NMOS. So here, parallel NMOS, we have the G1 transistor on this side and the G2 transistor on this side. Either transistor is connected if there is an input of 1 on the gate. Notice that because there is a parallel connection, there is a connection between A and B if G1 is 1 or G2 is 1 or both. So for these three cases, there is a connection because either G1 is 1 or G2 is equal to 1. For this last case, both are disconnected because both G1 and G2 are equal to 0. So there is no connection between A and B. So the logical equation is that solved by this is G1 or G2, implying a connection. So if we look at parallel PMOS now, here we're going to see a connection if and only if we have G1 equal to 0, G2 equal to, or G2 equal to 0, or both. So there are three possible combinations here where we'll see current flow. In the final case, either G1 is 1 and, well, both G1 is 1 and G2 is 1, then we see a disconnect between points A and B. So we have G1 prime or G2 prime, And by De Morgan's law, we have G1 ANDed with G2, quantity primed. So there is a disconnection if G1 and G1 are equal to 1. And by using this set of connection networks, we can implement AND gates and OR gates in digital logic. So returning to the inverter here, when A has a high voltage, PMOS is off and NMOS is on. When A has a low voltage, the PMOS is on and the NMOS is off. So only one of these transistors will be connected at one time or another. When A is VDD, or logic 1, what is Y? It is a logic 0. When A is 0 volts or ground, this is a logic 0. What is Y? It is a logic 1, like so. We can draw this as a truth table, as shown here. So when A comes in as a 0, here we connect this one and disconnect here. That gives us a logic 1 at the Y. When we have a logic 1 here at the input, this gives us a disconnection on the PMOS, a connection on the NMOS, and so logic Y, or the Y, is connected to a logic 0. For the NAND gate, to review, we have two transistors in parallel for the PMOS network here on top, and we have two transistors in series for the NMOS network. Notice it's parallel PMOS and series NMOS. This is for the NAND gate. So here, Y equals A ANDed with B prime. Right? Looking more closely here at the truth table, this is our PMOS network. Parallel PMOS series NMOS. So you have only one case when A and B are both equal to 1, where Y will connect to 0. So that comes in at this entry here. For the PMOS network, we have a connection from Y to logic 1. This is going to occur when either A is equal to 0 or B is equal to 0. So A is going to be equal to 0 or B is going to be equal to 0. So that will cover these three entries here. And we'll have a connection from Y to logic 1. Let's look closely at the NOR gate here now. It's similar to the NAND gate, but the PMOS transistors are in series. And the NMOS are in parallel. That means for this pull-down network, this NMOS pull-down network, it pulls Y to 0. There are three possible cases where Y is pulled to 0. Either A is equal to 0, B is equal to 0, or A is equal to 1, B is equal to 1, or both. So Y is equal to 0 for these three cases. The PMOS network is in series, so if both A and B are equal to 0, then we get a connection from logic 1 to Y. That gives us our single entry here. So the NOR gate, Y equals A or B inverted. So A is equal to 1 or B is equal to 1 or both inverted. So there's a relationship between the pull-up and pull-down networks that we need to consider, and it is that the PMOS network is always here above the output variable. And the NMOS network is always below the output in CMOS digital logic. Also, the pull-up network is going to be the dual of the NMOS network by De Morgan's law. De Morgan's law. Therefore, if PMOS in series, this implies that the NMOS in parallel and vice versa. Very, very important. We've only looked at the CMOS implementation of 2 input gates so far, but it is also 1 and 2 input gates so far, but it is also possible to look at multi-input gates as well. So, looking closely here, there is the relation between the pull-up and the pull-down network for the NOR gate. Here, notice that we have PMOS in series here and NMOS in parallel. So we are staying consistent with the rule that the PMOS network is the dual of the NMOS network by De Morgan's law. Some other logic gates and truth tables to review. Remember the OR gate and the AND gate. Let's look at the CMOS implementation of the OR gate here. Let's draw first a NOR gate. Like so. So we have our NOR gate here. We'll label the inputs A and B. A and B. Now we have an output from the NOR gate, but this needs to be inverted, so we get our OR gate. So let's draw the inverter here. And now we have our output Y. And we have an implementation of our NOR gate, or our OR gate in total. The AND gate is very similar, except that you exchange this NOR gate for an AND gate here. and the NOT gate or inverter stays the same. So let's draw that. Here's our pull-up network. A and B. Here's our pull-down network. Let's draw this a little bit more clearly here. Let's draw our ground symbol, label this VDD. A input, B input, again for our NAND gate. And then we pass this to an inverter here. Like so. And we have our NAND gate on the first stage and our inverter here, or NOT gate. So this is how you would implement an OR gate and a NAND gate in CMOS. We have our exclusive OR gate and our exclusive NOR, which can also be called the equivalence gate. Truth tables associated with those. So how can we implement an exclusive OR? Well, let's say we look at our truth table and we've got two possible cases. A is equal to 0 and B is equal to 1, or A is equal to 1 and B is equal to 0. Two cases where the output is equal to 1. So we'll say Y equals A prime B, or Y equals A B prime. So we can draw this as a logic circuit here. We need an inverter. An AND gate. Let's give ourselves a little bit more space. Above an AND gate. Here. And our OR gate on the next stage. Because we have this OR gate, we're ORing together two AND operations. So we have A ORed with B prime. We have, A prime or ANDed with B, like so. And we have an implementation for an exclusive OR gate. For the exclusive NOR gate, it's very similar. You can just place an inverter here on the front and invert the output. So we've worked primarily with two input logic gates so far. What about k input logic gates? So 3 inputs, 4 inputs, 5 inputs. Well, it turns out it's possible to do this in CMOS logic. So we could say we have a 1, 2, 3, 4 input AND. We could do a 3 input OR. We could do a 5 input NOR. Etc. Generally, due to the physics and uh, practicality of the situations, we have less than 5 inputs. So what does this mean here? Well, in CMOS implementation terms, what does it mean? Let's take a look at our 3 input OR. Let's try implementing this in CMOS here. Well, the first stage, we're going to use a NOR gate. And how do you implement an OR? In NMOS in parallel, PMOS in series. How many inputs? Well, we have 3 inputs. So let's place 3 PMOS transistors in series, like so. Now we need NMOS in parallel, so we'll place 3 NMOS transistors in parallel. Let's label our inputs A, B, C. A, B, and C. Now remember that we've got 2 connections for A and A on the PMOS and NMOS, so we have a virtual connection here even though I'm not drawing the connections, so please keep that in mind. And we also have the next stage, an inverter, or our NOT gate. Just place logic 1 and logic 0 to remind us here. And then our output, Y. So we can label our inputs A, B, and C and get our output Y, like so. So we also have De Morgan's law applied to gates. Let's take a look at our NAND gates. So if we have a NAND gate here, remember we can use bubble pushing. To change the shape of the gate. So this is A, B, quantity prime. Let's distribute this prime. Remember, the prime converts AND to OR and OR to AND when we distribute it. So A prime or B prime. If we were to draw this gate, We could do this, and we'd have bubbles on the input now. So this is for a NAND gate here. And you can draw the NAND gate two different ways. An AND symbol with a bubble input, or an OR symbol with or an AND symbol with a bubbled output, or an OR symbol with two bubbled inputs. This works for any number of gates, or for any number of inputs on the gate. So if I wanted to do, say, a 4-input NAND, this is the same as a 4-input NAND with bubbles on the input here. 1, 2, 3, 4. And our output. These are equivalent, right? These are equivalent. Let's look at the NOR gates. Well, this is the same as writing A or B inverted. By De Morgan's law, we can distribute this prime into the parentheses and get A prime ANDed with B prime. So another way of drawing this symbol, or this logic gate, is to draw two bubbled inputs with an AND symbol. The NOR gate can be drawn either way. So this is a multi-input example. Right here. And it's the same for NOR gates as well. So if I were to draw a 3-input NOR gate, I could convert that back and forth like so. To this symbol here. There are some alternative versions of XOR that you can use to implement circuits. Your exclusive OR does not have to be clean. You can also invert multiple locations. So if you look closely here, probably the simplest to understand is if you invert both inputs. So A and B on the input, well, what if you invert the inputs, A prime and B prime? Well, all you'd be doing is turning this whole table upside down, but notice that it's symmetric, so the functionality hasn't changed. If we invert either A, if we invert A, for instance, then we're going to have 1, 1, 0, 0, right? So this is going to convert the XOR to an equivalence gate. Therefore, if you invert an input, you need to invert an output to get the same possible functionality. And because it is an exclusive OR, it's symmetric. You can invert either input, and that implies you have to invert the output. So there are alternate versions of exclusive NOR or equivalence gates, so I encourage you to try exploring those with the truth table. And this ends the introduction of part 2 of CMOS digital logic.